Thank you for the invitation. Since it's the first talk, maybe it's good I'm going to speak about something rather simple, very old object, Leastsquare methods, but with a few new ideas and motivated by some approximation problems in high dimension, which I will explain. This is joint work with Giovanni Migliorati, who was postdoc in my institute and is actually now full-time member of the same institute. Okay. So let me start with describing two problems that motivated this work. The first one is not a high-dimensional problem. It's something that came out with collaboration with acousticians. And you see what you have here is a musical instrument. And what the goal was to recover mechanical information from the musical instrument, like the vibrating mode, from the acoustic field that could be measured by certain microphones. So you collect signals at these locations. And the first thing people do is to proceed to certain Fourier analysis in time and focus at a frequency of interest. Okay. Once they do that, once you have fixed the frequency, what are you doing? Essentially, you are collecting a function of the space variable at various locations, which are these microphones. Okay? You try to do something out of this. The second problem, which is now really a high-dimensional problem, comes from a topic that I've been working quite a lot in the last 5-6 years. So by parametric PDEs, I mean a partial differential which has a dependence on a certain parameter vector that could be of high dimension. So every time you specify the parameter vector, I guess if I point with the laser, it won't do anything on the screen. So every time you specify the parameter vector, you have a certain solution to the PDE which lives in some Hilbert space. And to take a concrete example, which I guess some people are familiar with here, you could look at the diffusion, steady-state diffusion equation on some domain and assume that your diffusion coefficient is piecewise constant on different subdomains. So you have a sort of composite material with different values. Okay? And these are now your parameters. So what you would like to understand is how these values affect the solutions. Okay? So now you have this map, which is high dimensional. Every time you take one of these x, you get a solution. And what you would like to do here is to reconstruct this map, capture it numerically, again from a few measurements. What are these measurements? Now they are particular instances of solutions compute for particular instance of parameters using some numerical solver, your favorite PDE solver, finite element, finite difference, finite volume. Okay, so what's the common point to these problems? Essentially, you are aiming at reconstructing an unknown functions from scattered data, and these measurements are costly because in the first case, every time you measure, it means you have to place a microphone. You cannot afford to put 10,000 microphones. And in the second case, every time you measure, that means you are solving a PDE and possibly using an expensive solver. Your measurement could be noisy, but problems will occur even for noiseless measurements. And this xi, the place where you measure, can be either chosen by us, then you have a certain responsibility, You have to decide well. Or they could be imposed to us. They could be deterministic or random. And the natural question that come out are, how should you sample? How should you reconstruct? So obviously, this is an ill-posed inverse problem. You can only give a meaning to that if you have some prior information. And here, prior information will be in terms of approximability. Why? Because these examples come from a certain model. In the first case, an acoustic model. In the second case, this diffusion PD. And the analysis typically shows us that there exist well-chosen linear spaces of growing dimension m such that your solution is well approximated by such space up to certain known tolerance. So think, typically I'm going to stay quite general, but these spaces, think of them as polynomials, but they could be much more complicated. They could be reduced basis space. They could be very ad hoc built spaces. And a prior, this may be unusual. Usually, sometimes people put prior on the smoothness of functions. But as some of you may know, smoothness and approximability goes match very well together. And so this is going to be our prior. Okay? And the norm will always be here an L2 norm with respect to some measure, which I will assume to be normalized as a probability measure. Okay, so this is my norm. Okay, so when we are there, it's quite tempting to use Leastsquare methods. Why? Because Leastsquare methods are some way of emulating at the discrete level the L2 projection. Okay, the L2 projection is out of reach. What does the Leastsquare method does? Takes a certain value of m less than the number of evaluation, and it solves this minimization problem where these w are some weights and these yi are the noisy or non-noisy observation. And this is what we call weighted least square. In the case where w equal 1, this is just standard least squares. Okay? You can view this method as an orthogonal projection of u into Vm in the sense of this Hilbertian semi-norm. It has the structure of a norm, but it could not. It could be 0 even if the function v is non-zero. Okay, which is induced by the sampling and the weights. Okay, this square is nothing else than that. So I will denote by Vn this discrete semi-norm. Is everything clear so far? I guess so. Huh? Okay, why people like Leastsquare? It's because it's extremely simple to implement. For example, you introduce a given basis of your space, and you search for your solution in terms of this basis. Then you land into a linear system where the matrix is this empirical Gramian matrix. I say empirical because it's based on the design point xi from I equal 1 up to n. And the right-hand side is given by this. So in fact, you see you have a Gramian of the basis in terms of the empirical norm, in terms of this discrete norm. And here you have the right-hand side. Okay? You know that the solution is always exists, but it's going to be unique in the case where this matrix is invertible, and we will discuss this shortly. Okay, so what are the general questions? Of course, how accurate is this? How stable is this with respect to data perturbation? And you see here you have two parameters entering the game. M is the dimension of Vm, so the dimension of the space where you build your projection. And n is the number of samples. And there must be some kind of interplay between these two quantities. The typical trade-off is, of course, that if m is too small, if m is very small, think of, that's the m, think of m equal 1, so think of just using constant functions, then you are essentially averaging everything. So this is very stable, but Vm has very poor approximation property. You cannot catch anything. On the other hand, if m becomes large, you gain in approximation property, but your method might become quite unstable. So m here, remember that it's always less than n. In the case where m reaches n, you are doing some kind of interpolation. You are exactly matching your data. And you know, for example, that polynomial interpolation can be quite unstable if you place your point in a non-clever way. So the question is now how to describe this optimal compromise. And of course, ideally, what would we like? We would like to have a stable and accurate approximation with a number of samples that does not exceed too much this the dimension m, right? This would be the optimal situation. And the question is, how is this going to depend on the distribution that we are going to choose? So I want to answer this question in a stochastic setting. And there are interesting questions on how, to what extent the result I'm going to give have a deterministic counterpart. So let's recall that we measure approximation in L2 with respect to a probability measure. This is our norm where we measure error. And what we're going to do is pick the samples according to some probability measure at random. But this measure will not be necessarily the same. So I'm introducing a second measure, mu, over x. And what I require is this relation between the two measures and the weight function. So I write it here. D rho, the measure for the error, is the product of the weight times the measure for the sampling. And W, remember, is the weight function that comes into this norm. And of course, the rationale is that as n gets large, you see that this norm is an empirical counterpart for this integral. Okay, it's just the expectation of this quantity with respect to d mu. And because of this relation, this is just the usual, the continuous L2 norm. In particular, the expectation of this quantity is this one. Okay? So, of course, the simplest case would be to just take W equal 1, standard Leastsquare, and then use the same sampling measure as the measure in which you plan to measure error. But what we will show is that there's a substantial interest in not doing that. Okay? And this, for people who are familiar, for example, with classical sampling method like in Monte Carlo method, this should remind them of a classical notion called importance sampling. Right? When you do a Monte Carlo average, sometimes you don't want to sample with respect to the measure which you are integrating, because the function that you are integrating has certain property. It makes no sense, for example, to sample in regions where the function takes 0 value, even if the probability measure doesn't take 0 value. Okay? So that is the same idea, but now applied to this problem, and we will see how it comes out. Okay. So what is our goal? We would like to compare the error of the least square approximation with the best we could do, which is the best approximation in this space. And since this is a projection method, intuitively, this comparison will be favorable if this method is essentially stable. Okay. So, all right, because you can think of this, you can think of this method to be exact for, since it's a projection error for the guys that are really in VM. So if you deviate from VM with this, you know that this should be good if the method is stable. Okay? Right. So in order to analyze that, we are going to use, for the analysis, an orthonormal basis of Vn with respect to this norm. We might not use this basis. We are not obliged to use it for the numerical method. For the implementation, we could use a completely different basis. Okay? In which case, you see that the Gramian matrix involved in the normal equation concentrates around the identity, because if you take the expectation, you have the integral of this with respect to d mu, so you just get the inner product of Lk, Lj with respect to this inner product. Okay? And therefore, what our analysis will rely on how far this thing can deviate from the identity in the spectral norm, which essentially amount in analyzing the condition number of this matrix. Okay? And we are going to discard typically the UW that could occur if this matrix is ill-conditioned. For example, this is something that we can, of course, inspect immediately. Ask if we deviate, let's say, by 1/2 or by some fixed number from the identity. And in that case, we don't trust the solution. We just set it to 0. It won't change anything on the result. Okay? So now we would like to compare this with this. Of course, this is larger than this, but if we could say that this is, let's say, less than twice this, or 1 plus epsilon times this, then we would be perfectly happy. Okay. Let's see. So now I come to the key ingredient in our analysis, which is the following quantity. So recall that this is an orthonormal basis for this norm, and we are going to introduce the following function. So we take the sum of the square of this function and multiply it by the weight. We call this function KMW. Maybe it's worth I write it. Actually, what will be most important is the sup norm of this quantity. So KMW, the sup L infinity norm of the product of W and the sum of the Lj square. Right. So let's look at this quantity for a second. And notice, first of all, that this is actually independent of the choice of the orthonormal basis, because if you operate a rotation, this will be invariant. Okay? This is just the sum of the square. So it essentially depends on 3 things. It depends on Vm, on the measure ρ, and on the weight W. Okay? How large or how small can this be? Well, it could be large, possibly, but it cannot be too small, because if you average it with respect to the measure d mu, you see that, in fact, you are obtaining the sum of the L2 norm for this norm of the function Lj. And because you chose an orthonormal basis, this is equal to n. So the average is equal to n. So the sup is certainly larger than m. Okay? This thing is always larger than m. It could be equal to m in some very particular case. And in the case where W equal 1, you get a simpler expression, which has an interpretation. It's called a Christoffel function. You see that this is essentially the diagonal of the integral kernel of the orthogonal projection operator onto Vm. Okay? It also has an interesting interpretation. It's the best constant that you find if you try to measure, to control the L infinity norm of a function by the L2 norm uniformly on the space Vm. Okay, so it has to do with what's called inverse or Nikolsky estimates, Bernstein-Nikolsky estimate. Okay. But what we are looking more generally is this quantity. Okay. So I'm going to give one sample result in the noiseless case, while we have analogous result in the noisy case that involve also the noise level. And they essentially say the following. They're going to give you the criterion that describes the trade-off between M and N. And the trade-off is described as follows. We are asking the condition that this quantity, the condition is that this quantity KMW should be less than some constant kappa times n up to this log factor log n. And remember that this is always larger than m. So what happens under this condition? Kappa here is something that depends on a parameter r that I can fix to be arbitrary. And under such condition, then, what I claim is that the method is going to be stable with high probability, in the sense that we don't deviate too much from the identity. And from this stability, you're going to derive the accuracy property here that I express here in the expected sense, in the mean square sense, by saying that this Leastsquare estimator is up to almost 1 times the best error, plus an additional term which accounts for the small events where you lose stability. Okay? So what does this mean exactly? It means that this condition is describing the regime for which, under which you have what you want. And this is getting quite demanding if this quantity KMW is much larger than M. Okay, we said that it's larger than M. In the ideal case where it would be exactly equal to M, you see that the regime is essentially that N is larger than M up to a logarithmic factor. Okay? This is what I'm writing here. So it at least imposes this condition, but it could be, in general, much worse. And there's, of course, quite a few variants to this result. You could put error bounds in probabilities instead of expectation, introduce some noise, but essentially, what I wanted is to put my finger on this important condition. So where does it come from? Well, it comes from a concentration inequality from matrix, at least in our analysis. If we inspect the matrix G that we want to control, you see that you can view it as an empirical average of independent copies of a random matrix of this form, where X is just a random variable with law described by the sampling measure. So you look at this matrix, this random matrix, which is actually rank 1 matrix. Its expectation is the identity, and you try to understand how its empirical average deviates from this expectation. There's all kind of bound for them. There's a famous paper by Joel Trop, which gives all kind of possibilities that generalize the standard concentration bound for scalar random variable, and the one we use is what's called matrix Chernoff bound by this, actually, which was introduced by these guys. What does this bound say? It says that, okay, here think of delta to be 1/2, so this constant C of delta is just a fixed constant. Then you have this exponential bound, where M is the dimension of the matrix, N is the number of samples, and K is an almost sure bound on the spectral norm of X. Okay. Now let's look at this X and ask what is its spectral norm. This X is in fact, you see, it's a rank 1 matrix, so it's just the product of a vector times its transpose. Okay. So its norm up to this W of X is just the L2 norm, the Euclidean norm of the vector square, so it's just given by this, okay? So when we look at the almost sure bound for this is exactly the quantity that I gave, KMW, okay? And now you see that if KMW satisfies this inequality, then you just put it in the denominator, and the 2n cancels out, but you still have the log n to give you this rate. Okay, that's essentially the origin of this. And now let me discuss, what I would like to go is to discuss this regime and what it means in relevant cases. Okay, and first I would like to consider the case, the unweighted case, to show you what could be a problem. Okay, so in that case, the stability regime is described by this, where Km is what we call the Christoffel function. And this Christoffel function is an interesting object. It's been studied in many important cases. For example, for polynomials in one dimension, there are interesting results that shows that the Christoffel function for Jacobi measure tends to what's called the equilibrium measure as n gets large. But so let's take a look. Take, for example, this very simple example where you work with univariate polynomial on -1, 1, and take the distribution which is related to the Chebyshev polynomials. If you take for rho this measure, then these polynomials Lj, the orthogonal polynomials, are just the Chebyshev polynomials. So the Chebyshev polynomials are very flat. They are cosines. Huh? That means that when you sum them up, essentially you scale linearly in M. Each of them has essentially norm 1 up to a factor. So you see that up to the log factor, you are in a very favorable situation. The stability regime is that the number of samples is barely larger than M. Now let's take a look at the uniform distribution, which is maybe the most natural one. Then the Lj are no more the Chebyshev polynomials. They are the Legendre polynomial that we know very well. Now, the Legendre polynomial, they are not completely flat. If you have seen what they look like, they tend to, they are small in the center and they get larger near the boundary points. And the effect of that is that Km, the max of this is going to be the sum of the value at the n point 1. And it's going to scale quadratically with M. So now you are in a much less favorable stability regime. And they are confirmed numerically. So for example, this is just 1D here. And we are looking at the probability empirically that the condition number is less than 3, which reflects the fact that you deviate by 1/2 to the identity. You are between 1/2 of the identity and 3/2 of the identity. Okay, and here you have n, the number of samples, divided by the log. You have m, and this is what happens with the Chebyshev measure. So you see that you have a kind of transition line, which is typically linear, where m is linear in n. Okay, and here what you see is that n, in the case of the uniform measure, n is, as we expect, should scale quadratically with m. So m scale like the square root of m up to this log factor. So we are in a less favorable regime. And now what you see on the right is something else, where we do something different here. We consider a new measure. We look at the case where x is the whole of R, and we take the Gaussian measure. This is quite a natural thing to do, which means that you are using the Hermite polynomials. Now, what you see in that case is that our theory is absolutely unable to cover this case, simply because these polynomials are unbounded on R. So when you sum their square, the L infinity norm will have no meaning, okay? And in fact, things are going terrible. You see that everything is black, but you see a very, very little strip here where you have some success. What does it reflect? Actually, you can do a little bit more ad hoc analysis that proves that stability holds, but under an exponential regime, which is absolutely unfeasible numerically. Okay, but this is actually what we observe. We cannot succeed unless the number of samples is the exponential of the degree of the polynomial. So something is wrong here, and we are going to fix this in a few minutes. But I would like first to go to the high dimensional case and to talk a little bit about parametric PDEs and how this applies to all that. So if you recall my prototype example of this piecewise constant diffusion field, you can view it in that form, okay, where A is some kind of average field and a linear combination of shape functions, and these are your parameters. So in my example, this psi j were just the characteristic functions of these subdomains, but this could be quite general, and we usually ask some uniform ellipticity assumptions such that this map, the PDE is well posed in H1, 0, okay? And we're going to do something a little bit similar here. We are going to approximate by multivariate polynomials. Now, because this map takes its value not on R, but in a Hilbert space, each coefficient in this polynomial will have values, will not be a scalar, it will be a function itself, okay? Or a finite element function if we work on some discretized grid, okay? So we have now more complicated spaces because they are high dimensional polynomial, and we have to choose carefully the index sets. So we're always going to ask something that these sets are what we call downward close, which is a very natural thing to assume for polynomials. We mean that if there is a degree which is represented, a multivariate degree, then the lower degree should always be represented, okay? That kind of makes sense. I don't know if I have a picture for that. Yeah. So imagine this set as you have degree in the first, degree in the second. Now our problem is to choose carefully this set. This is a high dimensional environment now, and this is our problem. Okay, so you can, when you do that, you can make change of basis. You don't need to use the monomial. You could use, for example, the Legendre polynomial or any other basis that you tensorize, and you keep only these degrees. And your question is how can you do that? How should you choose the degree? And can you use that to break what's usually called the curse of dimensionality in approximation, which tells you that in general, your approximation rate deteriorates as the number of variables goes to infinity. So this actually, that was my original plan, to give a lecture on this topic, but I thought this is too much focus on the particular applications, but I could talk for hours on this. So I'm just going to talk for 5 minutes, 3 minutes. Okay? So what's interesting about this problem? The interesting thing is that despite the fact that we work in possibly high dimension, infinite dimension, we can still retrieve a certain approximation rate if we choose very carefully these index sets, this polynomial set. But there is no free lunch. We need some assumption on that will be expressed on these functions psi j. Remember, the functions psi j are those that come here. Okay? It's quite natural that this function psi j should have some decay or some summability, because if you want that something like this holds, then this series has to converge one way or another when these xj are between -1 and 1. And so I'm being a little bit vague here because there's many, many different variants of this result. But this result tells you that if you have certain suitable summability condition on these, they will reflect into summability condition on the polynomial coefficients in the Taylor, Legendre, Hermite expansions of this map. And the consequence is that by selecting carefully the index set, you will be able to prove certain approximation rate. Okay? So the interesting thing is that in this result, the exponent is essentially robust with respect to the dimension d. Why? Because certain variables are less active than others. There's a lot of anisotropy. If psi j is very small for certain j, then you should be able to use less degree in the variable xj than in the other variable. And that's what's being quantified by this kind of theorem. Okay, now we want to apply our general results. So we have to consider now these complicated polynomial sets and estimate this quantity km. Again, I'm still in the case where I'm using a non-weighted Leastsquare method. And here are some interesting results. You can prove essentially that for the uniform distribution, the swing will behave like m squared. Actually, this is essentially sharp for all downward closed set. Regardless of their shape, what only counts is their cardinality. So you again land into the stability regime. If you use tensor product Chebyshev measure now, you don't have such a great thing as in 1D. It's not linear. You could have something like m to a certain power alpha. And this alpha, okay, it's smaller than 2, but larger than 1. Okay. And again, an interesting case is what we call log-normal diffusions, where A is not of the affine form that I gave, but the exponential of a Gaussian field. This is sometimes used by engineers to model very sharp contrast in the diffusion coefficient. Then you are exactly facing the same problem. You cannot handle the Gaussian measure. Okay, right. So this is what we are going to solve now by using these weights. Why? So recall that we sample according to d mu under this condition, and that our stability condition is given by this. Okay? So now let's do something which is completely obvious. We're going to pick the weights as the inverse up to this m of the Christoffel function. What does it mean? It means that d mu will be km over n times 0. It will just be, the sampling measure will be given by this. Okay? So this is indeed a probability measure, because you see that if you integrate, because each term integrates to 1 with 0, you get exactly that you get a probability measure. So this is what we propose. And what happens if you do that is that these two quantities simply cancels out. They give you m. Okay? So this looks quite trivial now. You have obtained a particular sampling measure and a particular weight such that the stability regime will always be optimal independently of the initial measure that you were taking. could be the Legendre, the uniform measure, the Chebyshev measure, the Gaussian measure, you name it. As soon as you do the right important sampling, in a sense, you land into the optimal regime, which first I did not have this intuition when I began to work on this question. And this is reflected, for example, for univariate polynomial. Here you have uniform, Chebyshev, and Gaussian, and now everything goes perfectly well. Okay, it scales linearly. So let me say a few things about this density. Now you have an optimal density, you see, and what's special about this density is that it's not anymore a fixed density. We're going to have to deal with that. It depends now on M. Okay, if you enrich the space Vm, this density is going to change. You see, it's given by this thing, and there are all kinds of issues here. Typically, in the case that I've discussed, parametric PDEs or other case, the measure d rho is usually nicer than the measure d mu because it's going to be a product measure. So it's easy to sample. D mu is not as easy to sample, but it's not so terrible. So in high dimension, what can you do to sample this measure? Okay, there are, of course, recursive measures like Monte Carlo Markov chains, which essentially generate, by recursive rule, a sample such that you approach asymptotically this measure. For this problem, we didn't have to do that. Actually, we can do something which is simpler, which is what we call conditional sampling, exploiting the fact that this rho is tensor product and this Lj are themselves tensor product of univariate bases in the case that we consider. So that allows you to have very simple form for the marginals. And what you're going to do is first sample the marginal for the first variable. Once you have sample, then you look at the conditional marginal for your sample for the second variable, and you go on like that. And this is rather simple to implement. It's actually more efficient in our cases of interest. So you can do that. The other issue here is that we are interested in all this business in what we call adaptive method, which is a setting where these spaces are not fixed in advance. They could be, but you're interested in updating them. Think, for example, of orthonormal matching pursuit algorithm or this kind of ideas where you have a certain polynomial space and you would like to, based on what you observe, what you have computed already as a least square, decide what should be the next one if you raise the number of samples. So typically what you are going to do is to look at some neighbor and some candidate degrees to increment and have some kind of a criterion. For example, in OMP, you match the residual with the new basis element to decide this is what we want to use our new space. And you continue, okay? And you keep the number of samples necessary to get the stability, so the optimal regime. Now, what is our problem? Our problem is that our measure is changing. So we sampled with a certain measure. Now we're changing the space. How should we deal with that? Should we sample back from the beginning with a new measure, or can we, one way or another, recycle the previous samples? Because this is, again, sampling is costly. For example, we don't want to have to do a lot of solves over and over again. Okay? And in that case, this can be done in a very simple way, but I was pretty slow to understand this. Just by the following remark. If you look at this measure, which is given by this, you see that it's just a mixture, a barycentric combination of the previous measure, where you didn't have the mth guy, and an update, which is given by this. So you can use this property to generate the sample in an incremental manner, right? You just assume that you have generated your sample independently according to the first distribution. Now, how are you going to generate your new sample? Just basically by rolling the dice, okay? And with probability 1 minus 1 over them, pick from this sample, and with this probability, pick from the update distribution, okay? So you move on like that, and the interesting thing is that you obtain a sequence of samples which is always reflecting the right measure, and you can prove that the total number of samples that you have used at the stage n from the beginning will, in expectation, satisfy the optimal regime. So you are essentially doing as good as if you were doing things from the scratch, but you recycle. Okay, and this is quite useful for adaptive algorithm. Okay, I'm basically done. And I see that I have no more battery, so I really should get finished. Okay, so this is the take-home message. You can do this to any measure and space. You want to use this now for the selection of lambda m. As I said, I don't really know how to give a deterministic counterpart to these results. These are some reference. This is the first paper that we wrote on that. And this is a general reference for these approximation results in for high-dimensional parametric PDEs. And this is a reference to the work I just presented. I want, by the way, do a little bit of advertisement for this journal, which is from the French Applied Math Society, which is completely free of charge for reader and for writers. Real open access. Finally, last but not least, yeah, this is an advertisement for those who are interested more generally in approximation theory. This conference taking place in June, I think, is a very interesting setup for cross-validation of ideas, and there will be quite an impressive list of plenary speakers. And the topic of high-dimensional approximation will be discussed in this conference. So thanks for your attention.